So today's topic is linear regression. It's our first machine learning technique. And as you can see here, we have a lot to get through. And like, honestly, most of the lectures this semester, I could easily spend 3 weeks teaching all of this. So in some parts, we'll potentially gloss over some of the details, but I will post some additional notes later that will go through some of the results in a lot more detail. For example, there are some derivations where we're going to just skip a lot of the tedious algebra, but I'm going to post notes later that go through all those intermediate steps that we might skip today. So you're free to review those later if you want, or ignore them if you're not into that kind of thing. Okay, so regression. Let's quickly remind ourselves, what is regression? Just a reminder about our Zoom etiquette in this course. So if I ask a question addressed to the class, feel free to go ahead and type in chat. You can also type comments in chat anytime you feel like it. If you have questions, if you have something you want to share. So what is regression? This is a quick warm-up question because it's very early in the morning for some of you. Last week, we talked about a few different categories of machine learning. We talked about supervised learning, unsupervised learning, reinforcement learning. And then we said that within each category, we could name a few types of machine learning problems, for example, regression, classification. What did we say regression was? Okay, very good. So regression is a machine learning problem where we're trying to predict a variable that is continuous valued, real valued. Okay, so we have some alpha variable y, it's continuously valued. And we're hoping to find some function that maps each input, x, to a prediction y hat, where y hat indicates that that's our estimate of y. And we hope that our estimate of y will be approximately similar to the true value of y. And then last week, we imagined a very simple regression model that predicts the mean of the target variable in the training data. So we said for every sample, we'll use y hat equals to W0, where W0 is just the mean of the target variable in the training data. So that looks a little bit like this. Here's our illustration. So this is what we looked at last week. We said we had this recipe for simple machine learning. We start with data representation. We took our data represented as, let's say, a vector. Then we propose a model. So in this case, our model was, y hat is equal to W0. We have our labeled examples of data. Next, we need to decide on a loss function. And last week, we said for this simple problem, we'll choose as our loss function, let's say the square, take the mean of the square of the difference between our prediction and the true value. So this expression y minus y hat is the difference between the true value and the prediction. We're going to square those, add them all up, and divide that by the number of samples. And since in this case, our prediction is always going to be y bar, this y with the bar on top denotes the mean of y, then that's just equivalent to y minus y bar squared, sum them all up, divide them by n. Now, under what conditions will this loss function be minimized? Or under what conditions will this be a good model? Right? We said a good model is one that has very small loss on the loss function, which measures how good the model is. And now I'm wondering, under what conditions will this model be good? So let's imagine we have some data set here. Okay, and on the vertical axis, I'm going to put y, the true value. On the horizontal axis, I'll put something x. Okay. Now, suppose I have a data set that looks like this. Is this model going to do well on the data set? Okay, no, why not? So let's see what this model will predict for this data set. For this data set, the model is going to predict the mean of y for all samples. So I'm going to draw the prediction of the model like this. So this is what the model is going to predict for every input sample. Is it doing a good job? Does it have a small value for the loss function? Okay, so I have some yeses, some nos. Let's take a look at how that loss function will turn out here. So for each sample, I'm going to compute the difference between the sample, which is the orange dot, and the prediction, which is the horizontal line. Okay, so for sample 1, the difference between the dot and the line is 0, sample 2 is 0, sample 3 is 0, sample 4 is 0, sample 5 is 0. So I'm going to square all those zeros, sum them up, divide by n, and I still have 0. For this particular set of data, this model did very, very well. Right? Now, someone said the sample size is low. Well, let's try a different data set with also small sample size. Okay. So maybe a very similar data set in a lot of ways. But now some of these values are different. Okay, does the model perform well on the second data set? So on the second data set, it performs less well. Let's take a look at, let's say, some of those loss function terms here. So for this first sample, here's the difference between the true value and the prediction. Okay, and it's fairly large. And then we're going to square that. We're going to do that for each of these samples and then take their averages. So here the loss function is non-zero. What is the difference between the first data set where the model did very well, the loss function was 0, and the second data set where the model did poorly, the loss function is bigger? What's the difference between these? Any ideas? Do we notice any differences between this first data set and the second one? Okay, so for the first one, the loss function came out smaller. Why is that? So let's see if we can answer this by forgetting data for a minute and look at this function. Does this function look familiar to anybody? Okay, does anyone know what this function is or what it represents? Okay, so this function here is actually just nothing fancy. It's just the variance. This is our definition of variance. So the mean of a sample mean of a set of data is just 1 over n of the sum of all the data points. And then the sample variance is 1 over n of the sum of the square difference between the data point and the mean. Right? So the variance measures how much data varies around its mean. Okay? And here our loss function is exactly identical to the definition of variance. Right? So as Greg points out in the chat window here, in the first example, y has no variance. And in the second example, y has variance around its mean. Right? So when a data set has no variance, and prediction by mean does a great job. But when there's some variance in the target variable, which of course typically there is, then a good model needs to be able to explain some of that variance. I'm emphasizing this variance idea because it's going to come up again and again today. Right? So here we can see that with prediction by mean, when there is no variance in the data, it's a great strategy. But if there is variance in the data around the mean, then we need a model that is somehow capable of explaining that variance. Okay, so let's see if we can identify such a model. Today, we're going to talk about a few different types of linear regression models. And the first one is called simple linear regression. Simple linear regression means just that you're doing regression with one feature. So you have a set of data that's feature label pairs. You have x's, which are scalar values. So each x is a single numerical value. And then we have y's, which are the target variable. That's what you're trying to predict. And we have n such pairs. Now we're indexing these with the I index here, but sometimes when it's convenient, I'll drop it. So don't get scared if I drop the index. Okay, and in our simple linear regression model, we're going to assume a linear relationship between the target variable and the feature. Okay. So previously, when we did prediction by mean, we just had a single scalar output for every y, we predicted W0. Now we're going to assume that there's a linear relationship between the target variable and the feature that's given as input, where we have W0 as a slope and W0 as an intercept, W1 as a slope in a linear model. And W0 and W1 are the model parameters that we fit in training. So we said as part of our machine learning recipe, we have some loss function, and then we train to minimize the loss, to find the parameters that minimize the loss function. So here we're going to train to find the W0 and the W1 that minimize the loss function. Okay. So let's just write out our new function here. We have W0 plus W1 x1. Okay. Now let's take this model and try and apply it to this very simple data set we had here. Okay, so I'm going to draw a linear model. We'll have an intercept, which means where it starts, and then a slope. So maybe I'll draw something like this. How does that look? Does this look like a good fit to the data? Okay, so it looks pretty good, right? Now, there's still some difference between, well, let's actually see. Where is a prediction for each data point? Okay. So for this particular sample here, where the true value is up here, what is my prediction going to be? Let's see. I'm going to put the predictions in purple. Okay. So where should I put this purple dot? What should be the prediction for this value of x? I'm going to start at the top and move down. Tell me when to stop. Am I going to predict here? No. Okay. Greg says on the purple line. So on the position on the purple line that has the same x value. Is this correct? Okay. So this is my prediction for, this is my y hat for this input value of x. And there's still some difference between the true value and the predicted value. Right? This difference is called the residual, by the way. So when I take the predicted value y hat and I take y minus y hat, so essentially this term inside here, that's called the residual. But we see that now some of the variance among the data is explained by the model. The part that's not explained by the model is the part that we call the residual. Okay. So here in this particular data sample, So I have this, let's say, blue line. Let's keep it orange, actually. Okay. I have this orange line here that represents how much this particular point varies around the mean. And then I have a model that explains some of this variance. So this part of the variance, the part that's represented by, let's say, a little green line, so from the mean until my prediction, this part is explained by the model. This part between my prediction and the true data point is not explained by the model. And we'll come back to this again today. We'll come back to it again on Thursday. So we have some variance in Y. We want a model that explains some or all of that variance. The variance tells us how much the data varies around the mean. The model explains some of the variance. So some of the distance between, let's say, the mean and the true value is predicted by the model, but the model does not explain all of the variance. So this point, this length between the predicted value and the true value is a residual, and the residual tells us what's not explained by the model. Are there any questions about that? So the residual term, which is this E here, captures everything that isn't in the model. So maybe in this example, there are some things about Y that I can't predict from X. And those things are captured by this residual term here. Okay, let's look at an example of a linear regression on some data. This is a data set of vaccination levels by county for counties in the state of Texas. And suppose we're going to try and predict vaccination levels. Maybe we don't have good data for all counties. We're trying to predict vaccination levels in various counties. And as the feature to use for our prediction, we're taking the vote in the 2020 election. Okay. So we're predicting vaccination levels by county using their share of vote for the Republican candidate in the 2020 election. Okay. So first of all, remember that a good model is trying to explain some of the variance in Y. In this example, is there variance in Y, or is it pretty much, constant at the mean? So what is Y here? Okay, so Y here is the percent of the population in each county that's vaccinated. Okay, so for example, for Travis County here, it's about 53%. For Dallas County here, Y is about 41%. Is there a variance in Y, or is it pretty much constant, like very low variance? Okay, so there's definitely some variance in Y. We can see the values of Y go from around like 75% all the way down to maybe 12%. So there's plenty of variance among the counties. Now, this diagonal line here might be a little difficult to see. Let me try, see if I can zoom in. No, okay. Okay, so this diagonal line here is a fitted regression model. Does the fitted regression model explain the variance in Y? I was trying to annotate this. Okay, so suppose the mean of this is somewhere around here. Okay. And the true values, obviously, we said have some variance, so they vary around the mean. And then this is a prediction of the model. The prediction of the model is this diagonal line. Does it explain some of the variance in the data? So in order to understand whether the model explains something, we're going to look at whether our data points are closer to the model prediction or closer to the, let's say, horizontal line at the mean. Okay. In this case, are the data points closer to the model prediction on average, or are they closer to the mean? So on average, I would say they're closer to the model, right? Even over here where you might have a data point that's very far from the model, it's even farther from the mean. And then you might have a few data points that are, actually closer to the mean than they are to the model prediction. But on average, most of the data is closer to the model than it is to the mean. So with that in mind, does this model have some value? Does it tell us something that we didn't have before? Yes, because it does a better job than prediction by mean. It has lower error than prediction by mean. And we know we can, let's say, take a look at, for a given sample, we can say what the residual is. The residual is the error of the model. How much of the variance in Y is not explained by the model. We can see for some particular counties, the residual is pretty big. So this one, for example, is very far from the model. For some of them, the residual is very small. So this county here, for example, is very, very close to the model. Let's change colors. Okay. What's an example of a county that's well explained by the model? So let's say Travis County over here is very well explained by the model. Presidio County here is one that's not explained well by the module because the magnitude of the residual is greater. Now, what accounts for data points that are not explained well by the model? Why are some data points explained well and some are not? Is it because maybe the slope of the line is wrong? Maybe it would be better if we had a different slope. Okay, so some counties are, let's say, high variance, that's true. But some of the counties that are explained well by the model are also counties that are far from the mean, and yet the model explains them well. So remember, the variance tells us how the data points vary around the mean, right? So here's an example of a point that's far from the mean, but still explained well by the model. So do you think you can predict everything about a county's vaccination levels just by looking at the county vote share in the presidential election? Okay, so there are probably other factors. Take Presidio County. Why does Presidio County have such high vaccination levels? Well, honestly, it's a very small county with about 8,000 people living in it. So if you have even, one or two people who are big vaccine evangelists and encourage everybody they know to get vaccinated, maybe there's a guy named Jim who lives there, who tells everybody he knows to get vaccinated and who's very convincing, and all of his friends are getting vaccinated. And so he's driven the vaccination level for Presidio County up. Right? So we don't have a parameter in our model that accounts for whether or not there is a man named Jim who's a vaccine evangelist living in the county, right? Our model doesn't capture everything that goes into determining why. Okay. So not everything about the target variable is actually captured by our model. So our model doesn't necessarily explain everything about the target variable, but we can see that it explains some of it because it has better performance than just prediction by mean. Okay, let's see how we can interpret this. So we have a slope and an intercept here. I'm going to focus on the slope. What does the slope mean? So here the slope is minus 0.4176. What can we say about the relationship between 2020 vote share and percent of population vaccinated using that specific number, minus 0.4176? Let's just say minus 0.42. Could we say that voting for the Republican candidate causes the percent of population vaccinated to decrease? Would that be a fair statement? Can we say that, let's say, an increase in the 2020 Republican vote share causes the vaccination level in a county to decrease? Well, does this model tell us anything about causality? Does it tell us that one causes the other? So Richard has a good point that there are other factors, but we know that this model explains at least part of the difference. So let's say if all other factors are held equal, can we say that an increase in the Republican vote share causes the vaccination levels to decrease if all other factors are held equal? So it doesn't show causality, not necessarily because counties are different, but just because this is not a method for identifying causal relationships. This is a method for identifying, let's say, what we might call associations. So based on this linear regression, we might be able to say the following. We could say a 1-point increase in share of Trump voters in a county is on average associated with a 0.4176 point decrease in the percent of population vaccinated as of this date. So we can't say it causes it. We can't even say it's always associated with it. So we can't say there will always be this relationship in every county. But we can interpret this slope coefficient as saying that on average, this is the size of the association between Y and X. So on average, a 1-point increase in Republican vote share in a county is associated with a 0.4176 point decrease in vaccination levels. What are the possible explanations for this association? Well, it might actually literally be causal, right? So maybe you could say, okay, maybe the Republican local governments have less aggressive vaccine campaigns. So that would be an example of a causal relationship. The 2020 vote has a direct causal effect on vaccination levels because the 2020 vote elects a Republican local government. But that's not the only potential reason. Other reasons are, okay, maybe there's some association like political values or partisanship attitudes are responsible for vote, and they're also responsible for vaccination attitudes in individuals. Okay. So maybe there's this association. Or there could even be what we call a confounding variable that's not even as directly related. So what if I told you that rural areas, so areas that are less densely populated, had a higher vote share for the Republican candidate, but it's also more difficult to distribute vaccines to rural areas. So that could also be potentially an explanation for this association. What if I told you it was a statistical fluke? Could it be a statistical fluke? Maybe this is not a true association, but it just happens to be in this particular set of data, they come out being arranged like that. Is that possible? So it is possible. The method that we're looking at, just computing the linear regression, looking at the coefficients, doesn't tell us whether the relationship is causal. It doesn't even tell us whether the relationship is a statistical fluke. There are other tools in statistics for answering both of those questions. All this tells us is that there is some association that we observe on average and nothing else. Okay, let's clear these annotations. All right, very good. So now that we've taken a look at that, let's look at slightly more complicated problems. So in the example we just looked at, there was only one factor that we said is associated with vaccination levels in our model. But we said that very often the one feature doesn't capture everything about the data. In our expression for simple linear regression, we have one feature, and we're trying to predict the target variable based on just that one feature. Now we're going to expand our model a little bit, and we're going to say, okay, now instead of having a single feature and a bunch of feature label pairs, now each input sample is going to be a vector. So we can represent our data as a matrix. Annotate again. Okay. So each input sample is a vector of inputs. So basically a row with D values in it. And it's also associated with a label. So the value of the target variable is the label. Okay. So we have a bunch of such samples. Each sample is a row and a label. And we stack all of these samples vertically. So they become a matrix. We have n rows in the matrix. N is the number of data samples. And we have D columns where D is the number of features. And then we have a vector Y, same as before, where we have one label for each sample. Now, we want to represent the relationship using a linear model again. How do we represent this relationship with a linear model? Well, we're going to need some more parameters. So our previous model had just one parameter, two parameters, an intercept and a slope. Now we have, sorry, that's actually a typo there. This is not a plus. Okay, so now we have a bunch of parameters. For every feature, we have an associated parameter. So we're going to represent the data as, let's say, the prediction for a sample I is going to be y hat I equals this intercept. We still have an intercept plus the first weight times the feature value for the first feature plus the second weight times the feature value for the second feature plus and so on, all up until the dth weight times the feature value for feature D. And this model will end up having D plus one parameter, so one parameter for each feature plus the intercept. Okay. So our samples are vector label pairs. We have a vector and then a label. And the predicted sample value for the ith sample will look like this. Now, in our manipulations of this matrix, it's going to be a little bit awkward to carry this W0 term around because it's kind of treated a little differently from the rest in that it's not included in this matrix. So let's try and roll it into the matrix. How do we roll it into the matrix? Well, we can actually treat it the same way as the rest, just by assuming that there is another feature at the beginning for each row. So remember, each xi is equal to x1, x2, etc., up to xd, like it shows here. Now, what if we imagine that at the beginning of every feature vector, there's just a number 1? Okay, let's call that number 1 x0. Can I put an imaginary x0 in here if x0 is 1 without affecting anything? Okay, so now I can just like slot a 1 at the beginning of every feature vector. And now I can kind of represent the feature vector as 1, comma, x1, and so on. And there's exactly as many elements in the feature vector as there are weights. So I can kind of slide that W0 into the rest of it by adding a 1 term to the feature vector. So let's do that. I have a new design matrix now, as we call it. So previously, my matrix for my data had only the feature values. Now I have a ones column in it also. And now my weight vector can include the W0 term. So let me annotate this again. Okay, so when we're multiplying this out to find y hat for, let's say, row 1, I'm going to take this term and multiply it by this term. Then I'll take this term, multiply by this term. Take all the intermediate terms, do the same thing, all the way up until this term multiplied by that term, and then sum up all those terms. So this is how I find y hat. Is this clear? Are there any questions? Okay. We can actually represent this using standard matrix operations. So let's do this. I know some of you might not have taken any linear algebra for a while, so you might not actually remember any matrix operations. Let's try this here. Okay, so I'm going to say copy in some values here. Okay, so suppose I have a matrix of data that looks something like this. Okay. Now I need to compute the matrix with the column of ones. So let's do that. I'm going to call it A. So take the same matrix, add a column of ones at the beginning. Okay. How many data samples do I have in this data set? Okay, so I have 4. Each row is a data sample. So I have n equals 4. And how many features do I have in this data set? Okay, so I have 2. Let's say d equals 2. Okay. Now I have this matrix A, and I want to compute y hat. Okay, so first of all, what are the dimensions of y hat going to be? How many rows, how many columns? Okay, so I'll have 4 rows. I'll have a predicted value for each sample, and I'll have 1 column because I'm only predicting 1 value for each sample. Okay. So we'll have our y hat equals okay. Now, in order to find y hat, I need a weight vector. How many elements will be in my weight vector? How many weights do I need? Okay, I need 3 weights because I have 3 columns in A. Now, we know that 2 of those weights will correspond to those feature values, and 1 of them is going to correspond to the first column, which is intercept. But that's fine, it doesn't matter. I just know that I need 3. Okay. Now, a little bit later today, we'll talk about how to actually find the best weights. But for now, let's just say my weights are 5, 1, and -2. Okay. Let's go ahead and try and compute the first element in my predicted output. So the first value here. So I want to predict what is the output of this model for the first sample, given these weights. Okay. What do I need to do? So I'm going to do a whole bunch of multiplications and additions. How many multiplications and how many additions do I need to do here? So I think I'm going to need 3 of each. So I'm going to take a bunch of these values, do some multiplications up here. And the result is going to go in there. Okay. So what numbers am I going to multiply? Let's change the color here so it's easier to follow. And this is just our basic matrix multiplication. What are the first 2 numbers I'm going to multiply? Okay, so first I'll take this, take this 5 and put it up here. And then I'll take this one, put it up here. So I have 5 times 1. Next, I'll take my second one. So weight 2 times x2 plus weight 3 times x3. Okay. And what value am I going to put into my prediction matrix here? Okay, so I'm going to end up with a 2. Okay. And then I could do this for every row. So just by doing these basic multiplication and addition operations, I can come up with my predicted output. Now, this is just, of course, an estimate of y. The true value of y is going to be still slightly different. So let's just represent it in terms of its shape. So the true value is going to be, of course, y plus some residual. Okay. So just like I have a vector of y's and a vector of estimates, I'll also have a vector of residuals. Okay, so this is my basic multiple linear regression. What does this residual look like? So before we represented the residual as the distance between a point and a line and the model prediction line. So here we said, let's say this blue value, which is the distance between the point and the model prediction, is the residual. What does a residual look like in multiple dimensions? Okay, so it has, let's see, is a residual a vector or a scalar value for, let's say, a given sample? So here I represented it as, let's say, a residual value for each sample. But for an individual sample, it will be a scalar value. So it's still just, let's say, the distance between my point and the true value and the prediction. But the prediction no longer looks like a line, right? So now that I'm working in higher dimensions, my prediction is not just a line. Now, if we have, let's say, 2 features, 2 dimensions, then we can still visualize it actually. So in 2 dimensions, the prediction looks like a plane. Right? So here we have 2 features, x1, x2. We have the true values, the y's represented as these red dots. And the model output is a plane. So this blue-green plane here is a model prediction. For any given point in this x1, x2 space, we can go straight up to the plane, and that's the predicted value of y. And then the residual is the distance between the true value and the plane. In higher dimensions, this is a hyperplane. I can't visualize it. But at least in 2 dimensions, we can still visualize the residual as a distance between the true value and the predicted value. Okay, any questions so far? Okay, so what could possibly go wrong? I have linear regression. The first simple version could only incorporate 1 feature, but now I can incorporate many features. Is there anything missing? do you think I'm going to be able to, let's say, capture everything that contributes to the variance in y in maybe any data set? Well, let's go back to our, let's say, reference data sets. Okay. And suppose y looks something like this. Okay. So y looks something like this. Do you think our multiple linear regression model will do a good job of predicting this value? No, why not? Okay, so we approximated our model as y hat equals, let's say, w0, w1 plus w1, x1. Here I just have x. But this function doesn't look at all like that. What does this function look like? Can anyone think of maybe a better function that would predict this? So our previous one was, y equals mx plus b, slope plus intercept. But this particular data set does not fit that well at all. Is there some other function of x that we think it looks better like? Okay, so maybe it's an x squared. Right? Let's take a look at an x squared. Okay, so it looks kind of like maybe an x squared between 0 and 1, right? Or maybe there's some exponential relationship going on here, right? So this model did not really do a good job. The linear model did not really do a good job of capturing this, because no matter how we draw a line through this data, it's just not really going to fit very well. So what can we do about this? Well, we could define a model like this, right? So we could just, let's say, okay, in our new model, f of x is w0 plus w1 x squared, or e to the x. Now, it gets kind of complicated. We don't want to do a lot of work to kind of analyze every model for every possible function of x that we want to consider. So next, we're going to see if we can kind of roll this whole thing into our linear regression model. Okay, so we're going to talk about what's called linear basis function regression. The linear assumption in our model, in our previous version of the multiple regression model, was very restrictive, because not all data will fit a linear function well. So what if instead of a linear function, we use linear combinations? So by linear combinations, I mean our model is still going to look like a weight times a value plus a weight times a value plus a weight times a value. So it's still linear combinations. But the values that we'll use in our model, let's say to multiply the weight, will be fixed, meaning I know them in advance, fixed nonlinear functions. Okay. Now we're going to call these basis functions. So let's say a function phi sub j of x is equal to that function with the entire x vector as its input. And we're going to call it a basis function. Okay. And now instead of having a matrix, so here we had a matrix where each entry in the matrix was just a x element itself. Now we'll have an intermediate step So where this, let's say, matrix entry is going to be something that was calculated from this entire row and then filled in here. So it's not necessarily just directly copying a value into a matrix anymore. Now we're going to compute each element in our matrix based on the row, and we'll use it as input to some function. So just as before, our model was linear in that y is equal to weight times the value plus weight times the value plus weight times the value. But now the value is going to be computed from a basis function, which takes the row input as the row vector as an input. Okay. Now let's note a few things about this. First of all, let's note that there is not necessarily a one-to-one correspondence between the columns of X and the columns of the new design matrix. So you can have as many columns as you want. What if, let's say, the first basis function is just 1? Okay. So that's actually helpful because we said, remember, we want a ones column here to account for the intercept parameter. Okay. So our first basis function is just phi sub 0 is equal to 1 for any input x. Maybe our next column is going to be x1. So remember, this x has two features, x1 and x2. I'll draw those. This is x1, x2. Okay. Maybe for, let's say the next feature, it's going to be x1. Next feature, we'll just use x2. But now we can have as many other features as we want, and they can be any function of one and of x1 and x2. So for example, we could have a feature that's equal to x1 times x2. Is x1, x2 a linear function? No, so that's a nonlinear function. But that's okay because it's a fixed nonlinear function and we can still plug it into a linear model. So our model is just representing this as a value. It doesn't care what the underlying function was. We can have any function we want here. So we have an x1, x2. We can have an x1 squared. So there's no one-to-one correspondence between the basis functions and the columns. You can have one basis function per column. You can have more than that. You can have fewer than that. You can represent the original columns again in the new data set or not, up to you. You can have nonlinear functions in here. That's also allowed. You can represent that ones column. That's very easy to do. And each basis function accepts as input the entire vector, the entire row vector. So now inside any column for row 1, you can put a value that's the value of a nonlinear function on row 1. Okay. How many parameters does this model have? So our previous model had as many parameters as there are features in X, plus 1 for the intercept. How many parameters does this model have? So let's say we define basis functions up from phi 0 to phi p. Right. So now we have one parameter per basis function. So as many as we define, that's how many parameters we have. What's the prediction of the model? Well, just as before, we're going to do a little bit of this kind of multiplication here to find the prediction of the model. where we're going to have a weight vector, just as before, with as many weights as there are columns in this new design matrix. And we're just going to multiply it out to get the prediction for each row. This kind of multiplying it out is what we know as the dot product. So that's what this notation here represents. This means that for a given prediction value I, you take each element in the weight vector, multiply it by the corresponding row element, by the corresponding element in the correct row of the design matrix, and sum those all up. And we can represent this basis function vector using this kind of vector notation. So here, phi is a vector where it expands out to the first basis function, second basis function, and so on, all the way up until the pth basis function. Okay. And just as we did here, we can represent all of this in a matrix. Okay. So we have a matrix here where, let's say, the first row will contain the basis function values for the first row of the data, all the way up until the bottom row, which will show the basis function values for the last row of data. And then we have p columns, one for each basis function, for as many functions as you want to represent everything about the data. And eventually you can represent this entire thing then as a matrix multiplication, just as we did here. Are there any questions about this representation? Okay, let's take a step back and remind ourselves, we had this recipe for, let's say, supervised learning last week. Okay. Step one in the recipe was get data. Okay. So now for linear regression, we know that it's a supervised problem. We're going to get data as a set of feature vector and label pairs. So we have n samples. Each sample corresponds of a vector of features and a label. Next, we're going to choose our model. The model tells us how we predict y as a function of x. So here we're going to predict y as the dot product of the basis function vector times the weight vector. Now, remember, we could make our basis function vector just be, the actual values of the features. We don't have to do anything complicated. We could, but we could just make, okay, phi of 0 is 1, phi of 1 is x1, phi of 2 is x2, and so on. We don't have to actually do anything nonlinear. Okay, what's the next step? Choosing a loss function. Okay, so now that we've described our model, and we described progressively more flexible versions of the model, we need to turn to steps 3 and 4, which tell us how do we find those weight parameters. Okay. So to find the weight parameters, we need to choose a loss function. And then we need to define a procedure, which we'll call a training algorithm. Then the procedure should find the model parameters that minimize the loss function. Okay. Once we do that, we'll then use those parameters to predict y hat for new unlabeled samples. And then we can evaluate the model performance. So we're going to start by finding the weight parameters for the simple linear regression. Now, even though we defined a more flexible version, and eventually we'll come up with weight parameters for this more flexible version too, we're going to start with a simple linear regression solution just because it highlights some interesting statistical relationships. And it's a little more difficult to understand those relationships in higher dimensions. So we're going to describe two methods for solving the simple linear regression. The first method is what's called the ordinary least squares solution. And it's called the least squares solution because we're minimizing a squared error function. What is the error function? Well, remember we had all these residuals, and error function means loss function, by the way. Okay, so we had all these residual terms. Each of these terms, y minus y hat, is a residual. Then we have squared residual terms. Squared residual terms penalize the model more if there are, let's say, a few values that are very far away versus many values that are close to the predicted value. So we're squaring those residuals, and then we'll sum those all up. So this expression is known as the residual sum of squares, or the RSS. Now, the residual sum of squares depends on n. Right? So if you have a lot of samples, even if each sample has very small error, it adds up. So you end up with a large value for RSS if you have many samples. Sometimes we want to be able to compare, let's say, different versions of the model trained on different number of samples. So it's convenient to have a loss function that doesn't depend on, let's say, doesn't always increase with the number of samples. So we could just take the mean of this, the mean version of this, and this is known as the mean squared error. So we're taking the sum of squared residuals and just dividing by the number of samples. This is our loss function. And remember that y hat depends on the weight vector, so we're going to consider this loss function as a function of the weight vector. And we're going to try and minimize it by finding the values of the weight vector that minimize this function. Okay. How do we minimize a function? So this is my objective function. It looks like this. How do I minimize it? Does anybody know any optimization? Okay. So this is a pretty simple function. And there is a nice rule about, what are known as convex functions. So if there is, let's say, just one minimum bet, and this rule tells us something about the derivative. So the derivative at the minima of a convex function, well, the derivative at any minima really is 0. So at this point here, the derivative is going to be 0. So to find the minimum of this function, which is a convex function actually, we're going to take the derivative of the loss function and set it to 0. Now, the loss function is a function of two variables, W0, W1, in this case. How do we take the derivative with respect to two variables? So we're actually going to compute what Michael pointed out is called the gradient. So we're going to take the partial derivative of L with respect to W0 and set it to 0. And take the partial derivative of L with respect to W1 and set it to 0. Now we're actually going to have two functions. These make up a vector, which we'll call the gradient. Two functions, two unknowns that we're trying to optimize for, W0 and W1. And so then we can solve for W0 and W1. So let's go ahead and do that. So now our recipe looks like this. We've chosen a loss function, and we're going to use this procedure of taking the partial derivative of the loss function with respect to each entry in the weight vector, setting it to 0, to find the model parameters that minimize the loss. The optimal model parameters will be denoted with a little star next to them, asterisk next to them. So W star is the optimal model parameters that minimize loss. Okay. All right, so let's go ahead and do that. This is our mean squared error loss function as a function of W0, W1. Here I wrote it out with W0 and W1 in it. And we're going to take the derivative with respect to W0, partial derivative, and set it to 0. Then take the derivative with respect to W1 and set it to 0. Okay, so what's the derivative of this expression with respect to W0? Let's start with the intercept first. How do I compute that derivative? So the derivative of this expression with respect to W0. First of all, is W0 constant with respect to the sum? Or does W0 have a different value inside each iteration of the sum? Do I have a different weight vector for each sample, or do I have one weight vector that I apply to all samples? Okay, so it's constant, right? W0 is constant with respect to the sum. So I don't need to worry about the sum. Forget about the sum for now. What would be the derivative of, let's say, minus x squared? Does anybody know how I can take that derivative with respect to x? So that's basically what I have here. I have, a bunch of other additive terms. Those don't matter for derivatives. So essentially, I'm left with minus x squared. What's the derivative of minus x squared? Okay, so this is minus 2x using, let's say, the power rule, product rule, chain rule, right? So first I take the derivative of this whole thing, given that it's raised to the power 2, I have 2. Then I take the derivative of the inside part using the chain rule. Now I have a minus 1. So using the chain rule, product rule, power rule, I end up with minus 2x. So that's exactly what I get here. Okay, so I take the derivative with respect to W0. I just get this whole thing with a minus 2 over n term in front of it. Now, when I set that expression equal to 0, I can drop that minus 2 factor. So it doesn't end up mattering too much. Okay. So now I set this equal to 0. Remember, when we set it equal to 0, we can get rid of the constant factor for convenience. And now I'm going to distribute the sum. Okay, so take this, put it in here, and here, here. Okay, so now I have this term. Let's actually clear all that. I have this term here. This is equal to the mean of y, right? Now let's look at the next term. So now I'm going to take this sum, distribute it in front of this. So now I have the sum from 1 to n of w1 xi. Okay. That term, once I find the optimal value of w1, which I will eventually, w1 comes out, so in front of that. And now I just have 1 over n times the sum of all the xi's. So that's just the mean of x. Okay. So now I can then just distribute that out. And the optimal value of W0 with the intercept is the mean of y minus W1 times the mean of x. So it's a very simple expression. Okay. So we found our optimal value of W0. Let's find the optimal value of W1, the slope. Okay. So I need to take the derivative of this with respect to W1. Now, it's similar to before, except now we have this extra xi term. Okay. So previously our derivative just looked something like this for the intercept term. Now I have this xi term in here also. And there's a whole bunch of tedious algebra in solving for W1. I'm not going to do it now, but I'm going to post some extended notes that go through all those steps if you're someone who likes that. If you solve for W1, you end up with this expression here. So in the numerator, we have, let's see, the sum over all the n's of xi minus the mean of x times yi minus the mean of y. And in the denominator, we have, again, the sum over everything of xi minus the mean of x squared. Does anybody know any special names for these quantities, either the numerator or denominator? Does anyone recognize any of them? The one in the denominator you might recognize because we just looked at it earlier. Does anyone know what that is? what's this quantity down here? Okay, so this is just the variance of x in the numerator, in the denominator. In the in the numerator, we have the covariance, exactly. So if we define the covariance like this, and variance like this, we can see that the slope coefficient is actually the ratio of the sample covariance to the sample variance. What does the sample covariance tell us about? Does anyone know what that statistic tells us about? So the sample covariance tells us something about how closely two values vary together. So to what extent is an increase in one quantity associated with an increase in the other quantity, or if it's a negative value associated with a decrease in the other quantity. Now, it's actually more common to express this, that relationship using what's called the sample correlation coefficient. So you could express the sample correlation coefficient like this. This is the definition of this correlation coefficient, which we call R. And then you can say that the slope coefficient is equal to R times variance of Y divided by the variance in X. Okay, so I'm not going to do that. Yeah, actually, I will. Okay, so we have a new number that we just introduced called R. We'll talk about it in a moment. I'm also going to introduce a second new number called R squared. So what if we go ahead and find the mean squared error for our new optimal weights? So now we know the optimal weights. We can plug those into our mean squared error expression. And we find that with the optimal weights, the mean squared error is equal to the variance in Y minus the squared covariance of xy divided by the variance in x. Okay. And we can rearrange those terms, so divide both sides by the variance in y. And now we have something interesting. So this expression over here is called the fraction of unexplained variance. So remember, the goal of our model is to explain some of the variance in y. Right? And we know that if we use prediction by mean, what is the mean squared error of the prediction by mean model? Right. So the mean squared error of the prediction by mean model was just the variance of y. So in this term here on the left side, this denominator, which is the variance of y, is how much error is there if you just use prediction by mean. And the numerator is how much error is there in our model. So this is called the fraction of unexplained variance. Of all the variance in y, what fraction of it is still left unexplained after our model accounts for the rest of it? What's the best case scenario here? What do we want this expression to be? Okay. How much unexplained variance do you want there to be? So this term over here that I circled in blue. Well, if we want all of the variance to be explained by our model, then we want the unexplained variance to be close to 0. Right? So ideally, we want the ratio of the mean squared error to the variance of y to be 0. Right? And of course, if our error is close to 0, then this ratio will essentially be 0. Right? But what this expression does is it kind of adjusts our mean squared error to how much variance there actually is in y to begin with. Okay. So if we have a function that's just doing prediction by mean, well, it's easy, but it will still have very low error if the variance of y is small, right? What would this ratio come out to be if we were just doing prediction by mean? So if our model was doing prediction by mean, this ratio would come out to be 1. Okay, so 0 is good. 1 would be prediction by mean. Is it possible for this ratio to be greater than 1? Michael says no, why not? What would it mean if the ratio was greater than 1? Let's go back to our examples. So we had some, let's take this one. Okay. So this is, let's say, a fit to this line, and it looks pretty good. So I would expect the ratio of this error to the error of prediction by mean to be small, right? Because the purple model has pretty small error. So the ratio of the error of the purple model to the error of the gray model is going to be close to 0. Now let's kind of turn this model. As I rotate the model, is this quantity, the mean squared error over the variance of y, as I rotate the model, is that quantity increasing or decreasing? So what happened to the mean squared error, which is the error of our purple model, as I rotate it towards the prediction by mean? So as I rotate it towards prediction by mean, this quantity is increasing towards 1, right? If the model is the same as prediction by mean, then the ratio of error of the purple model to error of the gray model is 1 because they're identical models. Right? Now, what happens if I then, okay, let's take the purple model again. What happens if I then continue to rotate the purple model? What's happening to the error now? Is the error increasing, decreasing, staying the same? Okay. So the error is the distance from, let's say, each point to the line. And we could see as a model, when the model is pretty good and fits the data very well, then that ratio of error of purple model to error of the gray model is about 0. If the purple model becomes similar to the gray model, meaning it does about as well as prediction by mean, then this ratio is 1. And if it starts to do even worse than prediction by mean, it would increase above 1, right? So then this ratio would be above 1. Let's take a moment and look at the quantity on the side. Okay, this ratio here on the side, this value here, is known as the coefficient of determination. So it's a covariance divided by variance of x times the variance of y. And it's known as r squared. What are the possible values for r squared? So best case scenario, we said this quantity here is 0. So what would be a good r squared? If the ratio on the left is 0, then a good r squared would be okay, so a good r squared would be 1, best case scenario. If our model has similar error to prediction by mean, then this ratio will be 1. R squared will be about 0, right? So for a very good model, R squared might be close to 1. For a model that's about as good as prediction by mean, R squared might be 0. What about for a model that's worse than prediction by mean? What will R2 be then? So let's say this ratio becomes greater than 1. Can I have a negative R squared? Okay, so as my model becomes worse than prediction by mean, R squared can actually be negative. Okay. Now, this is true if our model is not necessarily fit well to our data. But do you think the optimization procedure we just described would ever find a line like this? Is this line I've drawn here the best fit line? No, it's not, right? Is there any data set for which the best fit line is worse than prediction by mean? So our model, our linear model, technically includes prediction by mean, right? So you could just set all weight parameters except the first one to 0, right? If prediction by mean was a better fit than any other model, then you would just set the mean as W0 and all other weight parameters to 0. Right? So if that was optimal, you could do it in this model. This model captures that. So if you've properly optimized the weight parameters, then the worst case scenario is prediction by mean. If there's no relationship between X and Y, then the best you can do is prediction by mean. Then this ratio would be 1 and R2 would be 0. If you've somehow not optimized your model parameters, then this ratio could be bigger than 1, meaning you're doing even worse than prediction by mean, and R2 could be negative. Under what conditions might you, let's say, have non-optimal model parameters? Okay, think about that. Maybe we'll talk about it on Thursday. All right, so we've just introduced a bunch of complicated numbers. Okay, so we have the correlation coefficient R, we have RSS, we have mean squared error, we have R squared, we have our slope coefficient, and we have our intercept. I'm going to ask some questions. I'm going to ask you, which of these numbers depend only on the data and which depend on the model also? So which of these numbers are characteristics of the data, which depend on the model? And I'm also going to ask you, which of these tell us something about the goodness of our model? Okay. So let us start with correlation coefficient R. Is it a characteristic of the data alone, or does it also depend on the model? So answer this question with respect to the correlation coefficient R. I'll remind you of the definition of R. Let's see. Okay, so this is R. Does the correlation coefficient depend only on the data or also on the model? Take a few more seconds to answer. Okay, so most of you answered that it is a characteristic of the data, which I would agree with. Now, it's true that a linear model is not going to fit as well on data that's not as correlated. So it does tell us something about how, let's say, an optimal linear model would perform. But it doesn't really tell us if we optimize our model or not. It's a characteristic of the data, not necessarily a characteristic of the model. Okay. Let's look at our other quantities. Okay. So let's answer the same question for the slope coefficient W1 and the intercept W0? Is it characteristic of the data alone, or does it only depend on the model? So answer the question for the coefficient and intercept. Okay, take a couple more seconds to answer. Okay, most of you understand that the coefficient and the intercept is something we compute as part of training the model. So it also depends on the model. Now, does it tell us anything about the goodness of the model? So this is something where the class would split 50-50. Suppose the slope coefficient is large. Does that tell us that the model is a good fit or a bad fit? What does that tell us about the goodness of the model? So someone who thought it does tell us about the goodness of the model, maybe share your reasoning in chat. Does anyone think it does not tell us about the goodness of the model? Okay, no one wants to explain. I would say that the slope coefficient doesn't really tell us about how good the model is. It tells us something about the magnitude of the association that we're predicting, but it doesn't necessarily tell us how well it fits. Okay. What about, let's say, the RSS and the mean squared error? Let's relaunch this. Do the RSS and the mean squared error, are they characteristic of the data only, or do they also depend on the model? And what do they tell us about the goodness of the model? Okay, take a couple more seconds to answer. Okay. So the RSS does depend on the model and the mean squared error. They're actually defined as the error of the model. And of course, they definitely tell us about how good the model is. The smaller these quantities are, the better the model is. What about R squared? Is R squared only dependent on the data, or does it also depend on the model? Okay, take a couple more seconds. Okay. So this is one actually where, again, we're kind of split here. And I agree that that one is actually confusing, and I'll show you why I think it's confusing. So here we said that this ratio is defined as R squared. And this ratio just uses the sample covariance and the sample variances. So it looks like it's characteristic of the data itself, right? It looks like it doesn't depend on the model. On the other hand, we also said that it's equal to 1 minus the mean squared error over the variance in y, which is absolutely something that depends on the model, right? So we're actually going to have R squared that kind of does double duty. R squared is defined as that coefficient of determination, which is a characteristic of the data inherently. But it's also used to refer to this quantity of 1 minus mean squared error over the sample variance. And that quantity obviously depends very much on the model and tells us about the goodness of the model. Now, what we saw previously is that these two quantities are equivalent when we use the optimal parameters for our linear model. Okay. So when we use the optimal parameters, then we can say exactly how good the model will be as a function of the variance and covariance in the data. And in that sense, it's based only on the data. But of course, if we didn't use optimal parameters, then our actual error could be worse than predicted than you would think just from the data itself. Okay, let's take a look at a couple of quick examples. So this is the data on vaccination levels that we looked at a moment ago. And in this example, we said the slope W1 is equal to minus 0.4176. And we said that means that a 1-point increase in Republican vote share is associated with a 0.4176 decrease in population vaccination level of the county. And we said the R squared value is 0.5542. Is that a good value? Is this a good model? How much of the variance in Y is explained by the model? So there's some variance in Y. How much of it does the model explain? And how much does it not explain? Okay. So if R squared is 1, that would tell us that the model explains all the variance in Y. If R squared is 0, the model doesn't explain any of the variance in Y. That's just like the mean. Right? Here we can say the model explains a little more than half of the variance in Y. And then that fraction of unexplained variance, which is 1 minus R2, is about 0.45. So some of the variance in Y is not explained by the model. Let's look at another state. Okay, so this is the same data, but for Florida. Here, R squared is 0.42. What does that tell us? So for Texas, R squared was 0.55. For Florida, it's 0.4261. What does that mean? Okay, so this means that our linear model on vote share explains less of the variance in vaccination level in Florida than it did in Texas. Okay. Now, what does that tell us about the association? So we said that in Texas, a 1-point increase in vote share is associated with a 0.4176 decrease in population level. In Florida, is a decrease in population level associated with a 1-point increase in vote share bigger or smaller than in Texas? Let's put them side by side. In which state is the decrease in population vaccination level as associated with vote share bigger? Okay, so let's take a look at the W1 vector. So in Texas, there is a 0.4176 point decrease associated with a 1 point increase in vote. In Florida, there's a 0.4829 decrease in population level for each 1 point increase in vote. Okay, so the association is different in Texas and in Florida. In Florida, on average, we see a bigger decrease in population level for 1 extra point of Trump vote. On the other hand, the R squared value is smaller, right? So that tells us that although there is a larger decrease in population vaccination level in Florida than in Texas, more of the variance is explained in Texas than in Florida. So that essentially tells us the slope is steeper in Florida, but the points are closer to the line in Texas. Does that make sense? Okay. So R squared tells us how close are the points to the line, meaning how much of the variance is explained by the model, which is the line. And the weight parameter tells us the slope of the line. So how big is the effect? Okay. Let's do a couple of other quick things. So we did this least square solution for a simple linear regression. For a multiple linear regression, I'm going to go into even less detail. Again, I'm going to ask you to look at the additional notes for the details of the derivation if you're into that. But let's just take a look at what the solution looks like. So first of all, we're just going to define the norm of a vector. You hopefully remember some of this from linear algebra, but the L2 norm of a vector, it's often denoted with a little 2 up there, is equal to the square root of the sum of the squares of all the elements of the vector. Okay. And we also know that when we want to minimize a multivariate function, we take the gradient with respect to, which is the partial derivative with respect to each input, and we set each entry to 0, and then we get a system of equations. Now, how do we minimize the mean squared error for our multiple or linear basis function regression? Well, we have a vector, we have a n by d matrix phi, and we can define our loss function like this. Okay, so our loss function is equal to the L2 norm of the vector y minus the matrix phi times the weight vector. And I just put that half factor in there because it makes, some stuff cancel out. When we're trying to minimize something, then the constant factors don't matter anyways. Okay, so this is the L2 norm of y minus phi times w, and we're going to try and minimize that. This is equivalent to minimizing the residual. So we're really minimizing the norm, L2 norm of the residual. Okay. All right, so we're going to take the gradient of this. This actually, again, not going to go through it, but we get this expression here. And when we set it to 0, we find our weight vector is going to be the phi matrix transpose times itself. This is going to be a square d by d matrix. Take the inverse of that and multiply it by phi transpose times y. This has a unique solution if this is full rank, which in most cases occurs if n is greater than d. So usually we need to have more rows in our matrix, meaning more data points than we have features in order for this to have a unique solution. But if it is, then we have this unique solution. And we can rearrange it like this. And this gives us a set of d equations and d unknowns. And these are referred to as the normal equations. After this lesson, I'm going to post a short notebook that shows you how to compute linear regression coefficients by solving a system of linear equations. So using the standard linear algebra method for solving a system of linear equations. That's exactly what's happening here. So we have this expression sets up a square matrix, a vector, and then another matrix and a vector in exactly the same way as we would to solve a system of D equations and D unknowns. They're called the normal equations, and you solve it in the usual way to find the solution. Okay. So you can take a look at that notebook after. Now, there is one problem here. The problem here is runtime. Okay, so let's take a look at this solution here. In order to compute the solution, let's see what operations we have to do. So first we have to do phi transpose times phi. How long does it take to do that? Does anyone know? What's the runtime of that matrix multiplication? Well, let's take a look up here. Okay, so here we have a matrix with 3 columns and 4 features. Okay. How many operations did we need in order to compute one element in the answer? Okay. So to compute one element in the answer, we needed 2 times as many operations as there are columns here. Right? So the number of columns here is D. We have D equals 3. In order to compute one element, it's O of D. Right? And then in order to compute n elements, so we need to do this n times, 1 for each row. So it's O of ND. Right? Now, that was when we only need to compute, let's say, 1 column in Y. So this part, let's say, computing this, that will be ND. Right? What about this part? So this was multiplication of a matrix and a vector. Now we're multiplying a matrix and a matrix. So this is going to be even bigger because now instead of having to compute only 1 column of output, we'll need to compute n columns. So now we actually have O of, erase this. So to compute this part over there, we have O, D, and squared. So to multiply these matrices, it's the same idea as what we just did with, let's say, a matrix and a vector, but now we have to compute n more columns. Okay. And then we also need to compute this inverse. Okay. Computing the inverse, once we do this multiplication, we're going to get a D by D matrix. And computing the inverse using kind of standard ways is going to be, computing inverse using standard ways is going to be O of D cubed. Okay. Now, in practice, there are faster ways to do this, but if you would do this the naive way, you have O of D n squared, O of D cubed, O of ND. Now, we said that most often we'll have many more samples than we have features. So usually we'll have n much bigger than D. And n especially, we know if there are many samples to learn from, can be very large. So if n is large, then this term dominates, right? And finding these optimal parameters is O of Dn squared, meaning that asymptotically, if we have very, very large n, the number of operations we need in order to compute the optimal parameters is in proportion to D times n squared. So that can be a big, big number. What if we don't want to compute all that? Well, we have alternative methods for finding a solution that might be a little faster. Okay. Now, it's still based on the idea of the gradient. So the gradient has 2 very important properties for optimization. The first property is the one we just used before, which says that at a minima, the gradient is equal to 0. So you can take the gradient, set it to 0, solve that, and find the minimum. But there's another important property of the gradient, which is that at any other point, the gradient points towards the direction of maximum increase of the function. Okay, so here's an example. This is the error of, let's say, linear regression on 2 parameters. Okay. And the minima is down here, as shown by that red point. And if you compute the gradient on any space in this plane, it's going to point towards, let's find a good color. It's going to point towards the direction of the maximum increase in this error function. You compute it here, it will point there. And of course, the magnitude of the gradient will be larger if the increase is steeper. So wherever you compute the gradient, it points in the direction of the greatest increase of the loss function. The idea of gradient descent is to use this second characteristic of the gradient, okay, that it points in the direction of steepest increase in the loss function. And once you know where the loss function increases, well, you don't want the loss function to increase, you want it to decrease. So we're going to find the gradient and then go in the opposite direction. So this is called gradient descent. In order to move towards a minimum of a smooth convex function, we start from some initial random point. Then we iteratively compute the gradient at that point, add some fraction of the negative gradient to the current point, because we want to go in the opposite direction of the gradient, and then go there. And then now we're at a new point, compute the gradient again, add some fraction of the negative gradient, go there. So let's take this example here. Suppose I start here. I compute the gradient, it points up in this direction. So I'm going to move a small step in the opposite direction. Now I'm here. I compute the gradient, again, it points up. I'm going to go a small step in the opposite direction. And in this way, I'm going to iteratively move along the loss curve until I get to the minima here. Once I get to the minima here, the gradient will be 0. So then when I compute the gradient, I'm going to realize, oh, I can stop moving. And this is how we would express that mathematically. So we have a weight vector at each iteration, so for each t. And at each iteration, we compute the gradient given the current weight vector. And then we subtract some fraction of that from the weight vector, and that's our new weight vector. And we repeat this until we meet the stopping criteria, meaning the gradient comes out to be very small. How many operations do we need for each iteration of gradient descent? Okay. So how many operations do we need to compute the loss function for a given weight vector, x vector, and y? So there are d elements in the weight vector, d elements in x. And we're just computing, let's see, yi minus the dot product of the d length weight vector and the d length x vector. Okay. So that's just d multiplications, d additions. Okay. So each of these will be O of d. Okay. Now we need to do that n times. So we do that for every point. So now it's O of nd. Okay. So this is already less than our previous solution, which was O of d n squared. Remember, when n is very large, O of nd is much, much less than O of n squared. Even when n is not that large, it's still. Right? Now there is an extra complication here, which is, okay, it's O of nd, but we need to do it more than once. How many times do we need to do it before we find the solution? Well, we're not going to get into it here, but I'll post some notes later. But the answer is that you actually typically don't need too many iterations. So under most conditions, and of course, this depends on how you select this alpha, because alpha determines how far you move on each iteration. But if you set alpha pretty well, then you can actually get to a good solution without too many iterations. So then you end up with something that's O of nd. It's much less than O of d n squared. Can we do better? Well, if n is large, this can still be pretty expensive. So that leaves us to our next solution, which is stochastic gradient descent. Stochastic gradient descent says, okay, instead of computing n of these each time you move, you just randomly select one point, compute the gradient for that one point, and then move towards the opposite direction of that. So at each step, we compute the gradient using one sample and move in the direction that's the opposite of that. Now, sometimes we'll have steps that go in the wrong direction because one particular point might not point us in the right way. But on average, as long as the steps are small, we should progress towards the minimum. Okay, what's the runtime of this idea? So now, instead of doing n of these each time, we're just doing one of them each time. So what will the runtime be? So what did we say it is to compute the loss function for one weight vector and one input vector? And each of these have dimension d. Okay, so to compute this one time, we need O of d. Right. So it's no longer O of nd. Of course, we're still concerned with the number of iterations. So we might need more iterations. But as long as the number of iterations is that we need in order to reach a good solution is less than n, then we still come out on top. Now, of course, the number of iterations will depend on how much error you can tolerate. And I'll post some notes about that, and we'll also look at it more closely on Thursday. But we can see that this could potentially do very well. So we've gone from O of d n squared for the solution using the normal equations to O of nd using gradient descent, except it's not really O of nd because we need multiple iterations, but it's O of nd times something that's smaller than n. And then for stochastic gradient descent, we have O of d, again, times some number of iterations. But as long as that number of iterations is less than n, which it generally is, we've come out on top. Okay, there's one more variation of this, which is called mini batch gradient descent. And it's confusing because it's also sometimes called gradient descent. This is kind of a compromise solution, which basically says each time you move, well, you don't select one point, but you don't use all of the points either. Each time you move, you select a batch of, let's say, some number of points, and then you compute the gradient based on that. Okay, we're going to stop here. Sorry, I went over time again. We'll talk more about all of these concepts on Thursday. And on Thursday, we'll do a bunch of kind of demos and simulations to try and get a better intuition for all of this, and also to have some graphical intuition behind it also. We'll also talk about all of the things that might go wrong. So it looks simple, it looks like it works well, but what might happen? Finally, I'm also going to post some notes later this evening that will go into more detail about some of the derivations where we skipped a lot of the algebra and some of the other stuff we skipped. All right, are there any questions? All right, I will see you all on Thursday and have a great day.